Hello, everyone. Thank you for coming to our webinar this morning. I'm Ryan Murdoch. I'm the Director of Technical Marketing and Sales at Molecular Vista. I'm joined with my colleague, Tom Albrecht, who is the Director of Engineering and Technology at Molecular Vista. During the webinar, if you'd like to ask us any questions, there should be a chat box down below. Feel free to type it in at any time, and we're going to field those as they come in. If we're also going to have Q&A at the end, so we'll try to get to all the questions as this goes. Briefly, Molecular Vista was founded a few years ago by Sung Park and Kumar Wickramasinghe. Sung Park, both men go way back in this industry. Sung had co-founded Park Scientific years ago. Kumar has really invented so many modalities involved with scanning probe microscopy over the years while he was at IBM. He's now at University of California, Irvine, where he actually invented the technique that we're going to talk about today, which is photo-induced force microscopy. And so what does PiFM do? What it does is it gives you nanochemical information, and it's achievable routinely and on a wide variety of samples. And those are 2 points I really cannot stress enough, is how routine it is, how simple it is, and that it's a very wide variety of sample archetypes, such as polymers, for example. Here on the right, this is the lasers tuned to 1490 wave numbers. The green is polystyrene, so we tuned it to that absorption for the polystyrene. And Tom's going to get into more of the applications, but I just wanted to just show you 2D materials. These are all PiFM results, PiFM results, plasmonics and the visible. And so it really is quite a wide range. Now, how it works is that we use the AFM resonator to very sensitively detect interaction between the AFM tip and its image force. And we get the hyperspectral information by employing a tunable quantum cascade laser that's tunable from 800 to 1800 wave number. And I say that range with sort of an asterisk. Tom's going to give more information on that, but it's possible that if you are interested in wave numbers outside that range, this still could be a very usable tool for you, and so we should spend some time on that. And now, how is it different from other techniques? One, it does not require a far-field detector or a plasmonic tip enhancement. The spatial resolution does not vary with the thermal properties of the sample. And it's also very, very user-friendly. It's basically as simple as just using an AFM. And so what I'm going to spend the next several slides going over is unpacking these 3 questions of what does it do, how does it work, how is it different? And so the wish list is we want the chemical information. We want it to be much better than the diffraction limit. And ideally, we don't perturb the sample. It's non-destructive. And so how do we get below that diffraction limit and get the chemical information out? And so pictorially, what we're talking about. So if we have an AFM and we're taking topography, which you see on the lower left, and the colorful checkerboard on the upper left, that would be at each pixel, I think, a spectrum. And the answer is yes, we can. And that's what I'm going to get to explaining here. And so we got to go backwards a little bit. And so scanning tunneling microscopy and atomic force microscopy have both been around since the 1980s. And they provide topology, but not chemical information. However, they do get well below the diffraction limit without any problem. So the idea is, can we combine scanning probe microscopy spatial resolution with some sort of spectroscopy similar to, for example, FTIR? And the answer is yes, we can, but it starts with employing an AFM as sort of the engine. And from there are a few different ways to extract the chemical or spectroscopic information from the AFM. One is by illuminating a laser source at the tip sample junction to induce a near-field response, and then collect all of the near-field and far-field photons in the detector and employ some trick to discern near-field photons from far-field ones. So for TERS, the trick is plasmonics, which I'm going to get to, and for scattering SNOME, it's lock-in detection and clever modulation scheme. And another way to extract the cantilever is to get it directly from the cantilever's response. So we get the spectrum from the response to the cantilever. So this would be an example of mechanically detecting the optical response. So on the right, that's called PTIR, photothermal infrared AFM spectroscopy. And there, in that example, there's a pulsed mid-IR laser focused onto the tip. The pulse rate of the laser in that study was chosen to line up with the second contact resonance of the cantilever in contact with the surface. And the response is deduced by demodulating that frequency from the AFM feedback electronics. And spectroscopic information is acquired as the tunable laser source is swept through its range, as the cantilever response will change with wavelength, creating an absorption spectrum that typically correlates very well with the known bulk FTIR spectra. In that study, they showed 25 nanometer spatial resolution, but a more routine spatial resolution for PTIR is 100 nanometers. And so I've just outlined, so a scattering-based technique and the techniques that use the mechanical properties. And PiFM is an example of using mechanical properties, as I'm going to show. But if we would bin TERS and scattering SNOME in the examples where they collect the scattered light. And so ahead, I'm going to outline two of the scattering techniques, TERS and SNOME, and describe how they detect. And then I'll outline PTIR briefly, and then we'll unpack PiFM so you can clearly see how it contrasts. All of the techniques have their individual charms, and they complement each other well. So we'll just get deep in the weeds for a few slides to discern some of the finer details. They are fine details, but they do have important implications, and it's important to draw the distinctions. So in the case of TERS, as we show it here, it's basically just like confocal Raman with an AFM added on top of it. Here it's shown in the inverted geometry. And the basic thing is that you really have to have a plasmonic enhancement from the tip to see any signal at all. And the plasmon response from the tip creates a strong field enhancement in the tip sample junction. That enhancement amplifies the Raman shifted photons so they actually become detectable. Every trick you can play with TERS is going to help. For example, keep the tip close to the surface, so modalities like STM or shear force AFM tend to work the best. Polarization, if you can get it polarized so it's in the tip axis, that's desirable. Side illumination works fine too. And really the issue with TERS is the tips. If you etch 20 tips, one of them will show TERS enhancement typically. And it's very common to use a gold substrate ground plane to get the gap field enhancement. It's very difficult to get TERS signal, honestly. And so all the optimizations that one can do, one should do. And now scattering SNOME is another one that collects the scattered light. It's somewhat complementary to PiFM in that one is measuring photons and one is measuring force. Though they're different methods, they provide similar information with a lot of overlap. With SNOME, you can get the optical phase information and extract the real and imaginary parts of the permittivity through the use of an interferometer, like what's shown here. Here, the IRQCL goes through a beam splitter. It's focused on the tip. There's a Michelson interferometer reference arm set up to interfere the scattered light. And it's collected with this MCP, this far field detector. And so the near field is actually scattered into the far field by the cantilever's tapping. There's some far field that actually is also modulated by the cantilever. So even when you demodulate from the lock-in amplifier, you still have far field background, and there are other tricks like self-homodyne and pseudo-heterodyne to help eliminate some of the parasitic far field signal that I won't get into. The spatial resolution generally is about what the tip radius is. One of the downsides is it can be difficult to deconvolute signals if you have adjacent nanostructures present and they're close together. There is a spectroscopic component to it that I'm going to talk about on the next slide. And so here's these are nice results from this technique of nano FTIR. And so I'll briefly touch on some of the work where the spectroscopic component was added to an S-node. So with the tip and sample located in one arm of the interferometer, they illuminate the tip with a broadband source, either the QCL or the difference frequency generation from the fiber laser shown there. And they perform Fourier transform spectroscopy of the scattered light to get the spectroscopic information. But this is pretty low power that's scattered off the tip sample, low power illumination in this case too, of 100 microwatts. And so with such weak signal, the integration time is really long. So to get this one spectrum, that was about 60 minutes, and they averaged 154 frames. So transitioning to the mechanical side now with PTIR, what they do here is use a pulsed IR source, focus it on the tip, and the cantilever's ringing can be very well correlated to the absorption spectrum. So if you draw an envelope over the ringing that's created by the pulse source when it hits the tip, that actually is the absorption spectrum. And so it is simpler than turning an S-node in that you don't have to collect any light, but the spatial resolution is not as good. It's typically 100 nanometers. It requires you to be in contact AFM. And the resolution actually is the function of the sample itself, the sample geometry in terms of the thickness, and also the sample thermal properties, the diffusivity. And so having given that overview of the other scattering-based techniques and the other mechanical-based, so we transition now to photo-induced force microscopy. And so let's look on a very fundamental level how PiFM works. If you ask yourself the question, what is an AFM? The answer is simple. It's a resonator under feedback. And the resonance that's typically used for AFM is the F0 eigenmode, where the lever oscillates up and down. And that oscillation is fed into a lock-in amplifier. The lock-in amplitude or phase is fed into a feedback loop, which holds some constant value of a lock-in parameter. There are additional eigenmodes with the cantilever that we are going to put to use for PiFM. The F1 mode, which has a node in its oscillation, can be thought of as a vacant sensor that we are now going to occupy. So by modulating, so there's the F0 mode tapping, by modulating the laser source at some FM such that it sums with F0 to equal F1, we create a sideband at F1. So if we then follow F1, if we lock into it, that directly gives us information about the tip interacting with its induced image charge in the sample. And the reason that we choose to do this mixing as a sideband is we get, in general, we get better elimination of some of the background by doing it than if we just modulated at F1 directly. And so, and we can, yeah, and so here's another schematic showing it. So if you look at the feedback laser that's positioned over the cantilever, and then look at the detector, the waveform coming out of that, we're basically demodulating that in different ways. One way to get the topography, the other way to get the PiFM at a different frequency. And so the inset on the lower left of the PMMA polystyrene, basically the way we do the hyperspectral information is we tune this QCL to be on the absorption line of one of those or the other. And Tom's going to talk more about that. But this is a spectroscopic tool, and we are directly reading out the response from the AFM feedback electronics. And by working in the mid-IR, this allows us access to this molecular fingerprint region where it's so many, so there are a lot of resonances with some of these polymers and things. So briefly, I'll talk about the nature of the forces involved and what are we actually measuring. So as the incident light polarizes the material, it generates a standing dipole, and the strength of the dipole will be directly related to the polarizability of the sample tip system. So in reality, both tip and sample have a complex polarizability, and so really we're measuring that whole system. If you want to know more about the actual mechanisms of this, go dig out that reference. But basically, the local force is proportional to z to the fourth. It falls as z to the fourth. And so that's what gives us this really strong sensitivity, because it's actually it's more sensitive than the AFM interacting with the tip itself, the normal interaction. And so PiFM in the mid-IR, where the imaginary part of the tip dominates the real part, the force will follow the imaginary part of the absorption of the tip in the sample. And so I just want to, on a block diagram level, just outline the difference between scattering SNOME and PiFM. So in scattering SNOME, you have a laser source. It's directed through an interferometer. It's focused onto the tip, and there's a phase-sensitive monitor that's monitoring the cantilever position. You recollect the light, it goes back through the optics, and all the glass is going to have some loss to it. You collect it in a photodetector where you're collecting all the far field and the near field. You then demodulate that to get the near field signal. In contrast, PiFM, you go through the steering optics, focus onto the tip, and directly read out your near field signal from the AFM feedback electronics. So they are complementary techniques, though. It's like I had mentioned, with SNOME, you can get the complex optical phase information out, and so there is charm to both. And actually, on our Vistascope, we do provide both as options. But as I had said, there's no light collection necessary, no losses from the downstream optics, and no parasitic far field to separate out. And so I'll pivot now to talk a little bit about the actual platform before turning it over to Tom. The Vistascope, it provides optical access from below, from the side, and from the top. And so it really covers a really high amount of optical access. And the AFM is rock solid stable. And so oftentimes it's difficult to fit on all of these optical access paths from below, side, etc., because an optical microscope may be being retrofitted with an AFM. When our team designed the Vistascope, they had all of the paths in mind from ground zero, so they were able to develop an extremely stable AFM with all of the required optical access. And there's also a low vacuum enclosure, so you could pump it down to low vacuum or backfill with nitrogen. That helps tremendously with the water absorption lines that are pesky in the IR. And with the Vistascope, you'll always get the PiFM photo-induced force microscopy. With Vista TERS, we add TERS to that. With Vista SNOME, there are reference arm and other components that we add to it to give you scattering SNOME. But all are available. We have results on all of them, and we'd be happy to share any of them with you if you contact us. And so with that, I'll transition over to Tom.
Okay, very good. Thank you very much for that nice introduction to how PiFM works and the complementary modes. We'll be spending some time here now to show you what PiFM can do.
Mm-hmm.
And let me just bring up my presentation here. Get that ready to go for you. So we do have one question on the screen, which I'll address here for the moment. Someone had asked whether they could receive a copy of the presentation. And what we're going to do, we're going to post some content from this webinar on our website. And then if you'd still like to get something additional, you can send a request to us, and we'll see if we can send you some additional information. So yes, some content will be available from today's webinar. Okay, now turning to the topic of applications of photo-induced force microscopy. Spend a moment here showing just the basic capability of photo-induced force microscopy in terms of its resolution and so forth. And then right away after that, we'll turn our attention to what we call hyperspectral imaging or hyperimaging, a very powerful technique. So first, take a look at this slide. This is a combination of both a topographic image and some up here momentarily for technical. Okay, testing. Do we have audio?
Yeah.
Testing. Do we have good audio?
Oh yeah, it's just because I'm putting the echo on the speaker.
Turn this off, please. Okay, testing again. Good audio? All right. I have no audio. But that's okay. All right, so we're sorry about that very glitch there. Now let me share my screen from this computer. Okay, everything okay? Testing, 1, 2, 3. Okay. All right, so I understand it's working okay, and I'll restart this section since we may have lost a little bit of content there in that attempt to present from the other computer. All right, so I'm going to talk about the basic technique of PiFM, what it can do, what it can accomplish in terms of resolution and so forth, and then we'll turn our attention to what's called hyperspectral imaging, or hyperimaging, to show what that powerful technique can do. Here on this slide, we're looking at what's called a block copolymer fingerprint pattern. This was the sample that we looked at last summer that convinced us all of what PiFM could do in terms of delivering really a startling level of lateral resolution in terms of chemical mapping. What you see here on the top are 4 images. On the left is a normal AFM topography image of this sample. The sample shows not much detail. But then if we look at the remaining images, we're beginning to see the structure of this sample. A block copolymer like this forms alternating stripes of 2 different materials, one of which is the polymer PMMA, the second of which is the polymer PS, or polystyrene. If we tune the laser in our PiFM source to 1733 wave numbers, then PMMA has an absorption peak, and it lights up. You can see, for example, in that red image, all the areas where there is PMMA located. Alternatively, if we tune the laser to 1492 wave numbers, then the polystyrene has an absorption peak, and it lights up. If we combine those 2 images on the right, you can see that those 2 images are not the same. They are imaging alternate stripes of the material, and we're easily able to resolve these stripes, which are only 20 nanometers wide each, with a good signal to noise. Down below, you see some absorption spectra. In red is an FTIR, a conventional technique spectra of these materials, not on the sample, but on a homopolymer. If we just take a sample that's all PMMA, and then on the left, we get that red curve for FTIR. And the black curve is what happens if we do the same thing with PiFM. And you see that there's a good agreement between the 2 peaks, sometimes a bit more structure actually in the PiFM peak due to a number of different reasons. On the right, you can see the FTIR spectrum for polystyrene, and likewise the PiFM spectra. So there's good correlation between what we observe in PiFM in terms of absorption and what's observed by the conventional technique of FTIR. And what's neat here is the spatial resolution with which we're able to resolve this, which is really not possible by most other techniques. The next page shows another example of a very similar material, but even smaller. In this case, we've got a 24 nanometer fold pitch. So you can think of each of the stripes as being basically 12 nanometers. And so we treat this as basically a demonstration of achieving resolution in this 10 nanometer regime. Okay, but what about the vertical sensitivity of this technique? Here's yet another block copolymer system, but this one has been engineered differently. Instead of forming stripes of material facing upward on the substrate, this one forms layers. Each layer is 11 nanometers thick, and each layer is subdivided into 2 sublayers, which are 5.5 nanometers thick. On the right, you can see some schematic diagrams of how these are set up. The row of images at the top are what we call islands. The row of images at the bottom are holes. In either case, PTMSS is the material on the top layer. And you can see that, in fact, PiFM can resolve this and tell you which material is on top, even though there's only 5 nanometers of that material. So, for example, that top row of images, you see the topography on the left, which does show that 11 nanometer step properly. And then in the center top, if we tune the laser to 1493, then the polystyrene absorbs. So the background, which is polystyrene, is bright, and the islands, which are PPMSS, are dark. And then if we tune it to 1599, where PPMSS has an absorption, now you can see that the islands are bright. Similarly, in the bottom row of images, if you examine the schematic there, you'll also confirm that we are seeing the correct arrangement of the materials in this case. So PiFM has a penetration depth of several nanometers and is very sensitive to what's on the surface. All right, so now let's turn our attention to what we call hyperspectral imaging, or HYPER. This is a wonderful way to visualize what's going on a sample in terms of the chemical mapping and highlighting the individual materials that show up. HYPER basically means a very fancy picture which comprises a full spectrum at every single pixel. So not only do we get the topography, but at each pixel we get the full spectrum. So for example, if we look at this row of images at the top, and this is a sample which has a thin layer of PMMA as a background. It's only 2 nanometers thick, and yet we're able to detect its signature. And then we have little droplets of polystyrene sitting on top of it, which are about 5 nanometers thick. And what you're seeing on the top there are a row of images, and you see the little lines connecting those blue and red and green images to the spectrum below. And for example, you can see that the PMMA or red image was taken at 1731 wave numbers, which is a wave number where PMMA is highlighted. The green image, in contrast, is taken at 1495, which is close to a polystyrene peak. So there you see that those droplets are showing up brightly. The combined image allows you to look at both at the same time. Now, there's another thing we can also do, since we have this rich spectral information at each pixel, is we can look at some averaging over areas. On the lower left, you see a gray image with some shaded regions of red and green and blue. And that's allowing us to look at sort of the averaged spectrum in those areas. First, take a look at that green shaded area. That's just in the background where there are no droplets of polystyrene. So there we expect to see the PMMA signature peaks. And indeed, that green spectrum that the arrow is pointing to is exactly that. We see peaks at around 1730, which corresponds to PMMA. If we take the red one, which is focused right on a droplet, then you see a strong polystyrene peak in that particular case. And the blue one, likewise, a similar situation. Now, note that this only took us 54 minutes to acquire. There's actually equivalent to 400 individual PiFM pictures. That's because we have 400 wave numbers of spectral information acquired at each pixel. Okay, the next page here shows another mode that we can operate in. In this particular case, we've set up a little line of 6 particular locations where we're taking a spectrum. And here, as you walk across a droplet from PMMA on the left, up and over the droplet at about number 4, and back to PMMA on the right at number 6, you can see these various peaks come and go. Number 1, which is purely over PMMA, shows that peak for PMMA where we expect it at around 1730. By the time we get to number 4, we're seeing the polystyrene peaks much more strongly. So that gives you one more idea of how you can use this to take the detailed measurements. We can also superimpose the spectral information over the topography. In this particular case, you're seeing the same sample, and on the right, the bumps correspond to the topography that's being measured in normal AFM mode, and red corresponds to where we're registering spectral response for PMMA. Blue corresponds to where we're seeing polystyrene. And now you can understand the registration very clearly by plotting this particular mode. Okay. Now let's look at another thing you can do with hyperimaging. What we're finding with this technique, and this tends to happen when you invent and are able to exploit a new microscopy technique for the first time. It's really exciting. Pretty much anything you stick into this microscope, you see stuff that has never been seen before in this way. Any old sample off the street, or in this particular case, actually literally off the street. This is a sample of asphalt binder. The tar that's used for paving roads. And it's known to have 2 main constituents, asphaltenes and also maltenes. And as we look at this series of images, which is simply the individual PiFM images that comprise the hyperimage, and we're choosing a few interesting wave numbers where things light up. If you look at the top center, 1469, that's known to be a absorption peak of the asphaltenes, one of the known components. And indeed, it's very easy to identify that these flakes are the asphaltene constituent. Likewise, if we go to 1501 at the lower left, that's known to be a maltene absorption peak. And what you see there now is that the flakes are dark with no response, and the background comes up with a stronger response. Not so strong in this case because this has a little weaker absorption, but nonetheless, you can see the clear image reversal. And then what happens with these materials, as is often the case, if you simply sweep through all the other wave numbers, you'll find that all kinds of things are showing up as details. For example, in the upper left at 1528, we see all kinds of little specks lighting up. Likewise at 1433 below, or 1172, we see some little stripes at the bottom that weren't appearing otherwise. These are probably due to altered materials that have different absorption spectra, or in fact could be contaminants that may be present in the system, and that's often worthy of detailed study. The next image here, we've got a video, and this is what I find the most exciting to watch in the case of a hyper image. We're actually going to show you what it looks like when we sweep through the wavelengths of all the different spectral images that were taken during hyper imaging. So first, we're going to move our band, which is registering for the green picture. And now look at that picture as it shifts and changes its character as we move along to the band of wave numbers that we're using to generate that image. At this case, we've parked on a spot that highlights the background or the maltenes. Now with the red, we're sweeping along the same range, getting the same kind of image changes. In this particular case, we're going to stop on a location that gives us a nice response for the maltene flakes. And then finally with the blue, sweeping along, and in this particular case, we're going to try to highlight something that shows those little contaminants or altered material specks that appear on these asphaltene flakes. And when I see these types of images, it reminds me of the early days of scanning probe microscopy when we used to sort of marvel at the types of atomic resolution images we could generate. This isn't atomic resolution, but it's equally satisfying in that we're seeing stuff that's never been seen before at this level of detail. Okay, now one of the things that might surprise you is when we looked at the asphalt binder sample, one of the wave numbers we chose to image was 1501. And if you look at the various spectra associated with it, nothing has an absorption peak at 1501. So why is this a good wave number for looking at the maltene's background? Well, it turns out, and this is something you learn as you explore these images, the best imaging doesn't always coincide with a peak for the individual components, because sometimes other components also have absorption at those locations. If you look on the right, that's a bulk FTR spectrum of the maltenes versus asphaltenes. And what you see is right below 1500 there, or actually it's slightly above 1500 to the left. That is a place where the blue curve actually comes up over the red curve. In general, the red curve has higher absorption all the way through this area, but not at this particular wave number. The blue comes out. And likewise, if we do the same thing with PiFM and take the spectra over the two materials, you'll find that indeed, right around 1501, we do see the orange curve, which is the background, come up above the flake signal. So it takes a little bit of experience to learn how to highlight the various different constituents. But once you understand this, you know how to exploit this technique to give you the maximum understanding of what's happening and to map the chemical materials as best possible. Now, one question that often comes up is our Vistascope doesn't tune the full IR range. And that's due to a limitation in the types of tunable lasers that are available on the market that work well with PiFM. The particular quantum cascade laser that we're using only tunes 800 to 1800 inverse centimeters. And if a chemist who's used to doing FTIR looks at this, he might say, well, I'm missing some of the wave numbers for the peaks that I consider most important. And these two spectra you see at the top here sort of illustrate that issue. if you look at alkanes, the CH stretch peak on the left there around 2971, 2863 is sort of a monster absorption peak for this particular species and is often the preferred peak when searching for this. Likewise, on the right, carboxylic acids, another very important material species, has peaks in the same region, which we cannot tune. But it turns out that this is really not much of a limitation at all because, for example, both of these species also have smaller resonances within the band that we can tune. So, for example, on the left, although we can't see the CH stretch mode, we can see the CH scissoring mode there at 1470. Make a note of that because I'm going to show you in the next image how we actually use that to see these materials precisely. And on the right, if what you're after is carboxylic acids, you can use the C double bond O stretch mode at 1721 or one of those other modes that's indicated. We have good enough signal to noise ratio that these other peaks, which you might consider somewhat weaker, still show up loud and clear in our signals. So obviously, we will continue to advance our tool as laser technology improves so that we can tune a wider range. But nobody should feel at the moment that 800 to 1800 inverse centimeters is not enough to basically get the job done on basically every material that is of interest. So here's an example of this. This is acidic methyl ester. It's got the CH bonds, which you'd normally like to detect at, say, around 1300. But in fact, we can see them very nicely at 1463, which is that scissor mode I just mentioned a moment ago. So at the top row of images is topography, and the bottom row of images is PiFM. The one on the left is simply where you see the orange background. That's just tuning to the substrate absorption. So that shows up, and the little droplets there are showing up as dark. This particular sample was prepared by dissolving a small amount of this ester in a solvent, coating it on a substrate, and letting it evaporate. It forms spontaneously these beautiful little flowerets of material, which are just 4.7 nanometers thick. So again, this also demonstrates the sensitivity of the technique. The second image there, you do see a little bit of response at that 1463. And on the right, as we zoom into one of those, again, the lower right shows that we get a response. Now, it turns out this particular material has a very high vapor pressure, and it sort of disappears while you're imaging it. That's sort of unique to this particular sample, but that's why you see, for example, in those last two images on the right, that the little flowers has gotten a little bit ratty looking. One needs to optimize the power level and so forth. Even looking at a material like this. But other materials which are more stable, as I show on the next page, well, in a moment, let me get to that in a moment. I just wanted to point out here on this page that the peak that we used is indeed the CH scissoring mode. And this is the PiFM spectrum that's seen on that particular material. And that's how we got that image. The next page shows a similar type of material where we have polyethylene present, and we're using exactly the same CH scissoring mode to detect this material. This one's a little thicker, it's harder, there's no issue at all with it evaporating on the fly or anything like that. And here we get a wonderfully strong signal. The background in this particular case is polystyrene, and the droplets are low-density polyethylene, which also has that same CH mode. And as you can see, when we tune to 1466, the green image, those little round areas of polyethylene show up very nicely. And again, we can combine the topography and chemical information on the right. And you see an interesting amount of structure on this sample where we've got these droplets, or actually sort of islands of LDPE, but they also contain little sub-islands of the polystyrene and so forth. So once again, a very rich sample to look at. Okay, the next image here is of star polymers. So this is an interesting sample we got from some IBM colleagues. It's a material that has a polystyrene core surrounded by sort of this pom-pom or pendant structure of methacrylates. A normal AFM image, and this was taken by the IBM folks on the right, shows sort of the structure of this stuff when it's sort of dispersed in what is basically a monolayer of these core shell star polymer entities. And the question is, can we actually directly observe this core cell structure? It's quite small, and the answer turns out to be that yes, we can. These images are only a half micron across, 500 nanometers, and you can see that the individual molecules of the star polymer are definitely sub 100 nanometer structures. And indeed, when we tune to 1493, we get the blue response, which is clearly showing the polystyrene cores very clearly. And when we tune to 1720, we can see the surrounding pom-pom or pendant structure. This image has sparked a lot of interesting discussion in terms of trying to understand how those pendant structures are arranged, whether it's really a symmetrical sphere or whether they're lying down sort of flat and so forth. We'll leave that kind of discussion for another time. But the bottom line is you can see these structures in startling detail in that combined image showing the pink pendant structures and the blue core structures. Another one here is an example of what you might be working on in an industrial research lab. This is a multi-layer polymer stack that we got from a professor in Korea. And it has two types of polymers stacked up. And what's interesting here is rather than just looking at the top surface of this stack, this sample was microtomed. It was these little layers were put into an epoxy resin and then sliced to a very thin layer. In green, you sort of see a schematic of how this is done. The little red lines indicate little sheets of this material, and it's been sliced perpendicular to those sheets. And the little blue picture at the bottom is an optical microscope image that shows what these things actually look like in terms of being embedded in this epoxy matrix. This particular material has distinct absorption bands for the various materials present. And the question we're trying to answer on this one is the interface between the two sharp, or is it a little bit blended with some interdiffusion occurring between the two layers? And what you see is if you use PiFM, you can actually analyze the intermixing of these two layers at the interface between them. What we've shown here on the left is as we're imaging across the boundary, we've taken 19 different spectral points here spatially. Each one is only 12.5 nanometers apart. We have the resolution to actually see distinct spectra at each of those points along the way. And by comparing the peak heights of the two different materials, the P degta and the SDIB, we can draw some conclusions to the effect that indeed there is some intermixing at this particular interface. We won't go into all the details, but we'll give you a hint here on the next page showing a bunch of these spectra and how we were comparing the different peak heights at these locations to give us some indication of the relative levels of each of these materials as we traverse that interface and draw some conclusions about the level of intermixing. Okay, so now to finish up, basically just going to show you a couple other materials. You've seen lots of sort of polymeric materials up to this point, but also biological materials are a natural fit for this technique in terms of being able to see the absorption of individual species. This particular one is a nanofiber material, which is coated with nanocrystalline cellulose. On the left is the topography, and you can see the single strand of the pan fiber. It seems to have some sort of circular striations going around its perimeter, these little bumps along it. If we tune to the pan absorption at 1465, as you see in the center image, that simply shows us what is basically uniform fibers. If we look at the nitrocrystalline or nanocrystalline cellulose on the right, there we see that it looks like that one does show this modulation that corresponds to those little rings along the fiber that you see on the left. So we can surmise actually that the NCC does have this interesting nanostructure along the fiber. The next page shows another very important species, biological. This is collagen molecules. And in this case, it's not the usual fiber bundle that's often imaged, but these are the individual strands of collagen on a mica substrate. And here again, we can resolve these very nicely. You see the topography in sort of the 3D image shown here. And the red is the PiFM response tuned to 1666, which is the amide 1 absorption peak. And the collagen gives us a nice response at that level. And what you can see is there is good correlation between the topography seen in the AFM and the amide 1 absorption peak, indicating that indeed we see the absorption associated with these individual fibers. And if there were another particular material of interest present here, we could probably differentiate the two very nicely. All right. In summary then, PiFM generates IR spectra with nanometer scale spatial resolution. And this is ideal for chemical mapping of molecular materials, such as organics and biological materials, at a scale much smaller than conventional techniques. Really seeing things here that really have never been seen before. Hyperimaging is a powerful mode which generates and stores a full spectrum at each image pixel. And when you do that, individual chemical species, they light up at specific wavelengths depending on each material's IR absorption spectrum. Choosing to image at known IR absorption peaks often provide strong imaging response for a specific species, but sometimes off-peak wavelengths also provide a surprising contrast based on the relative absorption differences between species. Spectacular PiFM images have been shown on both polymeric and biological materials, as I showed you in this series of images at the end. And one thing we're looking for is we welcome additional samples that can demonstrate sort of new horizons and new applications. We have some ideas for a sample that can show some spectacular results and open up PiFM into a new class of materials. We welcome you to mention those to us, and we may indeed be willing to take a look at those and see what PiFM can do on some of your samples. Okay, so that concludes our webinar. And we certainly apologize for the technical difficulties that occurred in the middle. This is our first webinar, so we're learning here things that can go wrong. We will take a look at questions that have been typed in and address some of those if there are any. Okay, so I think it looks like the main question that came up was whether you have copies of the materials, and those, as we mentioned, will make some things available on our website, and you're also welcome to contact us directly with these types of questions. If you'd like to contact either Ryan or me, our email addresses are simple and straightforward. It's Ryan or Tom at molecular-vista.com. All right, thank you very much. Oh, we do have a few more questions that came up here. One more that says, does PiFM work well in a liquid environment? That's a great question, because naturally when you're thinking of biological materials, you'd like to take measurements on them in an environment that's of particular interest for the materials, and that is liquid or various electrolyte solutions and so forth. And the answer is, it appears that PiFM can work in liquid. We've done some imaging that has been successful in liquid. However, we don't emphasize that yet at this time. This is still in its infancy, and there are some disadvantages to operating in liquid in terms of damping with the cantilever resonance, which can lower the signal-to-noise ratio and the ability to pick up weak signals. So we're still exploring that, and we hope to have clearer answers on that in the future and be able to tell when we can successfully use imaging in liquid and when we can't. But for now, we would emphasize that there are lots of great applications that work in air, and that's the way to go for now. And we'll keep working on the liquid and hope to bring you some very interesting results on that. Another question that's come up is, can we use this to look for crystallographic information, such as grain orientation or dislocation? And here I would probably exercise some caution. Our lateral resolution is around 10 nanometers right now. We do have indications based on the theory that we would expect to have higher resolution as we continue to perfect this technique. For example, right now we're using metallized tips with a fairly thick coating of metal on it that ends up sort of increasing the radius of the sharp point of the tip. But anyway, where I'm headed with all this is that we really don't have atomic resolution today with PiFM as it works currently. And therefore, if one wants to take the most straightforward way to look at grain orientation or dislocations would be to sort of observe the lattice directly and then see the individual atoms in their lined up rows and so forth. And that's not something that PiFM delivers easily today. There could be other techniques that are not quite so direct. So for example, we have looked at layered materials like graphite or molybdenum-sulfide, and then often you can pick up things by looking at step edges and so forth to understand what might be going on in the grain structure of that material. Sometimes you'll also see symmetries in the arrangement of defects or even in the PiFM response or other types of optical responses that we've looked at. And sometimes you can surmise something from the symmetry you're seeing in those when you've got a particular rotation state, for example, in a free-form symmetric lattice. But those are somewhat indirect techniques. So bottom line is we don't promise that you can directly view atoms and see the lattice that way, but you may be able to pick up some indications. Is it possible to collect Raman data mapping? The answer to that is yes. We do offer the option of doing a confocal Raman measurement system. And so you could contact us for more detail about that after the webinar. But we have, in fact, demonstrated some very nice Raman imaging on various samples. And so you can use that complementary technique to gather some information in PiFM mode. And then, for example, if you've got this option capability on your instrument to look at it again in Raman mode, and obviously topography is happening there as well, and learn to correlate the results that you're seeing between those various different techniques. Okay, another question that has come up is what vacuum level can you get to with the enclosure? Okay, so this is a low vacuum enclosure. We're not at all trying to get into, say, what we might call a surface science environment where you might want to have, say, 10 to the minus 8 torr or better. That's not at all the objective of what we're doing with our vacuum chamber. The purpose of the vacuum chamber is twofold. Number one, first of all, just to get the air out of there, because air contains water vapor, and water vapor has some significant absorption peaks in the tuning range we're interested in. So one of the things you can do is simply evacuate it, or if all you want to do is knock down the absorption of water, actually backfill with a dry atmosphere, such as dry nitrogen or something like that. And then you can image in that particular mode. So we think that's a very useful mode. The second thing that we're trying to accomplish with vacuum is to increase the sensitivity of the measurement method. The Q of the cantilever rises when we have a vacuum. Even the low vacuum, say 10 to the minus 2 or 10 to the minus 3 torr, is more than sufficient to actually take the cantilever basically all the way to its maximum Q that you're going to get. The Q can increase by something like 10x, and that has the potential to offer a higher sensitivity. And we believe this might be a route to using thinner coatings on our tips, allowing higher resolution, and so on and so forth. So I'd invite you all to stay tuned for what we can demonstrate with the vacuum environment in the future. A number of things need to be worked out there in terms of imaging speed and signal-noise ratio and so forth. So that's still fertile ground for a lot of fundamental work. But that's the whole intention behind this, is first of all to get rid of air and water, and secondly to allow the low vacuum for Q increase of the cantilever. But as I said, not a surface science environment. Okay, another question that I see here is, do you expect the PiFM spatial resolution to increase in vacuum? And I think I did address that actually in answering the last question. The bottom line is, yes, we actually do, because we think it's going to allow us to investigate different types of coatings on our tips and sharper tip geometries. One thing I should point out is that basically the data you're seeing here is just with plain old off-the-shelf gold-coated cantilevers from the most prominent vendor out there. So there's nothing very special about the tips that we're using in this technique. And the success rate with these commercial tips is very high. Certainly more than half of them give you a nice PiFM image. Some folks would say it's as high as 90%. I'm not sure I'm fully convinced it's quite that high yet, but it's very good. This is not a difficult technique to do. But as we move to tip types that have thinner coatings and sharper tips and so forth, it's possible that vacuum is going to play an important role in achieving the maximum resolution that we can achieve with that type of a tip. So stay tuned, and hopefully in the future we'll be able to give you a lot more information about that. All right, I think that has answered all of the questions that came in. So we appreciate it that you typed those in. Those were interesting ones that probably a number of people were curious about, and also allowed us to fill in information on a few topics that we might otherwise have overlooked. So I think with that, we will conclude today's webinar. We thank you all for joining today. We plan more webinars in the future on various topics of interest for the techniques that we offer. So thank you very much, and goodbye for today.